All right. Right. Um, I want to continue thinking about the problem I mentioned last time, meaning the divisibility properties of the sum of orders of the cyclic group of order n. Um, and last time I showed sort of one key property, namely, well, first of all, I claimed without proof that S of n, the sum of orders of group elements of the cyclic group of order n, is multiplicative. And I showed how it evaluates on prime powers, but I didn't prove that. I only proved that it has specific. I proved that it has the value it has on single primes, but not general prime powers. And I haven't proven that it's multiplicative, so that's the one step that is missing. So I will try to think about that today. I'm not really sure how to do that. Then the other thing I wanted to think about is to prove the statement that I had last time, namely that if I look at the value of SP, then it is never divisible by a prime that is 2 modulo 3. And I'm not sure what I should start off with. I think I'll start off with showing, well, let's start off with something that I can show or believe I can show, namely the second part, the proving that S of P is never divisible by a prime that is 2 modulo 3. So let's do that. And then after that, I will, oh, sorry, let me quickly fix something. Okay, there we go. And after that, I want to show how one can use this to get a lower bound on the asymptotic density of the numbers for which n does not divide S of n. All right, so the claim that I want to prove is S of P, which we know to be equal to P to the power 3 plus 1 divided by P plus 1, which is also equal to this quantity here, alternating finite geometric series, is never divisible by a prime. Oops. Not sure what happened there. It's never divisible by a prime. Q such that Q is 2 modulo 3. So last time I got stuck way too long on the fact that I, for some reason, zoomed in very much on the fact that I wanted to look at primes that are either plus or minus 1 modulo 4, but that wasn't the right thing to do. And one thing that I hinted at is that, okay, the sort of reason why is because of this power here. So let's see. And again, this is something that I have proved before, but this is a very long time ago, and I'm not exactly sure how the proof went. So how do we start? Let's see. So we want to show that this does not hold. Okay. Mod Q. And from now on, I'll be assuming that Q is really 2 modulo 3. Okay. So this is a statement that we want to show. And of course, we have here a fraction, right? But the nice thing is that we know that we can expand it like this. So this this thing here makes sense. And okay, I mean, one sort of obvious thing, and we don't really need modular arithmetic to show this, is that we can cancel this part. Yes, and maybe to make it more precise, we're looking at modulo q, which is a prime. So as long as let's see. Okay, so let's quickly rewrite it like this. I want to assume that this is the case. Um, I want to say that we can just write this. And the reason is that, let's see, the inverse of 1 over p plus 1. Let me write this as follows. P plus 1 inverse. Um, unless this is 0, this always makes sense. Modulo q, because we're working in a field. Right, because modulo working a prime number, we get a field. Let's see. So I'm just worried about the. So this is for sure fine if this is. This is not equal to 0. Modulo q, and let me see if is there a good reason why this should be the case. This is not obvious because what could I have? Okay, let's choose some prime that is 2 modulo 3. So let's choose, I don't know, 5. And can I have a prime such that if I add plus 1, it is 0 modulo 5? Well, so the question is, does this hold? Mod 5. Or in other words, we want that p is -1 mod 5. That's still fine, right? There's plenty of primes that have this. Let's write down an explicit example just to double check. 19. So what is the issue there? So of course I could just write it like this and not have to worry about any of that, but that is not what I want to do, because sort of this expression here is just a little bit more complicated, I believe. And I also remember that my original proof was sort of based on just this quantity here. Okay. Okay, let's just sort of deal with this later. So okay, let's just write this as this implies that either 1 is 0 mod q, or p plus 1 is 0 mod q. And we should put here inverses. Okay, I feel like I'm missing something very basic here. Let's just move on to here and let's see how much progress we can make. Okay, so the question is, I am working in some field modulo q, right? And we ask, when we have some number, when we raise it to the power 3, do we get a -1? Now, if Q is 2 modulo 3, okay, so let's choose 5, for example. I'm going to think of these as roots of unity, so I can think of them geometrically, and I can think of them like these points. Of course, they should be equidistant, right, in the complex plane. But I can think of these as the roots of unity, fifth roots of unity, and I'm asking now, okay, I want an element in this such that if I raise it to the third power, I get out -1. Um, and let's see. So I mean, the argument I want to make here is that, okay, that doesn't work because there is no -1 here, right? But I also want to be careful because this seems to suggest that this argument would hold true for any prime q, or at least any odd prime, right? Because then we have an odd number of such guys, and then -1 doesn't exist. So that is slightly concerning. I guess maybe also one observation that we could make is that, okay, if such a solution would exist, then we could always also find, like we could choose a, oh, actually, that's maybe not true. That is not true. My bad. That doesn't have to be the case. So am I missing something here? Okay, so maybe it has to do with this denominator. What I'm going to do is I'm going to, let's see. Wait. Okay. Of course, yes. Okay, that's the. We don't need to think about modular arithmetic or anything. If you want to show that this is never divisible by a prime q that is 2 modulo 3, it suffices to show to hold it holds true for the numerator, because afterwards we are dividing by some number, which will only make it less divisible, and it won't sort of somehow add extra divisibility. It won't add any factors, right? Because here I will get some integer that I can write down the prime factorization of. Same thing for the denominator, and the denominator will just cancel some of these terms. Okay, so it suffices to prove it for the numerator. Okay, that's a good first step. And it might be, of course, that there will be cases where this is divisible, or there could be in principle setting where the numerator is divisible by a prime that is q, that's 2 modulo 3. And then the denominator is divisible by a prime as well. And so those will cancel out such that S of p is not divisible by such a prime. But what I'm claiming is that's not the case here. Okay. Now I'm a little bit baffled by this, because this seems kind of bad, and this would suggest there's never a solution, which is clearly false, right? Let's take an example. If I plug in a let's just take a prime. Let's take p is 3. So then I get 28, which is 2 times 2 times 7. Let's double check. This is 1 modulo 3, right? So that's good. Why doesn't this work? This argument here. So okay, let's say I now say, oh, okay, I now take q to be, let's say, 7, and I have 1, 2, 3, 4, 5, 6, 7. Okay, that's actually, I expected this to look worse. Still looks kind of bad, but okay. And then still -1 does not exist to look q. So what is the the problem here. Okay, so that argument clearly does not work. Oh, let's see. Let's see the wait. Uh, okay. Do I have it? Hmm. Okay. I am not really seeing it. And as I mentioned in the beginning, and also from what I remember from my proof, it really had to do with this 3 here. And that doesn't really show up in this argument as well. So let's start from scratch. This argument doesn't work, and at the moment I don't understand why it doesn't work. Right? At least it shouldn't work, right? Because it seems too powerful, and it would prove something that would be too strong, namely that this argument, that this is never divisible by any prime, which of course is silly. Okay, so we can remove this part here. So okay. Yeah, so what we want to show is actually the other way around, right? If we prove this statement, doesn't hold, then this also doesn't hold. That's what I want to show. Okay, let me just slightly rewrite this equation. Again, I'm not sure if this will help. Um, Now, okay. I can really interpret this as, let's see, -1 should be the only uh, wait. So I wanna, since I have a power here, I would really want to interpret this as a root, as some, as q's roots of unities. So I have some element p in, uh, let me see, it's a little bit annoying. I'm not sure what notation to use for like the cyclic group of order n, but I want to use here in particular the sort of the roots of unity. So I'm not sure what is good notation. Let's skip this for now. Um, this is so weird. I don't see what goes wrong with this argument. Okay, let me just be silly and let's plug in here the following. We know that we can rewrite P always in the form. Sorry. Let's put in here a 3 times B to the power 3 plus 1 is 0 mod Q. So I don't like doing this, but I don't really see another way to quickly proceed. So let's expand. Let's see. Oh, I'm very bad at this. I'm just going to be ask Matanska because I don't want to make any mistakes, especially late at night. So we just plug this in. Yeah. Okay. So obvious, of course, but whatever. All right. Now, does this help us? We know that Q is 2 modulo 3. I don't no, I don't see this. Okay, let me try another approach. So I want to sort of zoom out a little bit and look at the roots of unity, of the Q's roots of unity. And then I raise something to the power 3. So in roots of unity, this just means that mm, no, that also doesn't work out. What was the example that we had? We had, if we plug in PS3, we get out 28, which is 4 times 7. This is annoying. Okay. So I guess I know it's easy for me to just sort of get lost in thoughts, which makes for a terrible video. Might make for good math, but at least a terrible video. And it's also not what I want to be doing. So let me try to think out loud more. What I'm stuck with is the following. I remember this proof using really this framework of the roots of unity. And the nice thing about the roots of unity is that, when I take powers, okay, yes, when I take powers, then that just becomes multiplication. Am I saying that correctly? I'm actually not sure. What I feel like I'm getting stuck on is that I'm sort of, mixing the different ways of representing the groups, the cyclic group or integers modulo a prime. So let's try to phrase it in this picture here. What does this mean? I have your minus 1. Well, if Q is, okay, yes. If Q is 2 modulo 3, then this guy here means, okay, no, this is really just um, Oh, let's see. That doesn't. Oh, that doesn't necessarily work. I wanted to say, oh, that means it. This means it's 1 modulo 3, but that's not true, I believe. Wait, let's double check that. If I plug in, let's take some primes. Excuse me. No, that should be fine, I believe. Right, so this is just short for, okay, this is equal to minus 1 plus some k times q. We know that q can be written as 2 plus 3. Let's use j. So expanding this just gives 1 minus plus 2k. Okay, this is getting a little bit messy again, but well, whatever. Let's try. Plus 3kj. Now, okay, is this nice or not? No, this doesn't look really nice. But let's keep it there. Maybe it'll be useful later on. Okay, let's try something else. I'm now wondering if this has anything to do with Fermat's little theorem, which is a statement I should know from the top of my head, but I do not. So let me quickly check. Theorem. Okay, let's see. So let me just write it down. Let me write down a maybe more general case. Euler's theorem. Let's see. Oh, okay. Wait. I think I may have it. I see. I see. Let's say I have such a proposed solution. Then we know that 1 minus p to the 3 is just minus p to the 3, which should then be equal to 1 modulo q. And we want to, so okay, now the question is, okay, so this must mean, because for any element, p or whatever in integers modulo q, I can always take the minus. That's always well defined. So the question is, can I find an a such that this is true? Okay, so now we're making some progress, although I'm again a little bit worried that some of these statements might also be fine. I see. I see. I think I may have it. Yes, if I look at now when I have something like this, I can just look at the multiplicative structure. Oh, actually, okay. No, I was wondering maybe I can just directly apply Fermat's little theorem or Euler's. What is it? Euler's theorem. But that's not necessary. Okay, the argument is as follows. The question is, okay, when does there exist a third root of unity? modulo q, right? So when does this equation hold? And this is a little bit nicer because now we have a +1 here instead of a -1. And when I look at the, let's see. So I think the argument is as follows. If I look at the, first of all, I can restrict to A being non-zero because I want A to be invertible. Otherwise, I can never get out a 1. And so we say that, okay, A, we can really think of as living in ZQ invertible elements. But we know this is isomorphic for Q of prime at least to, yes, okay, to the cyclic group of order Q minus 1. Aha, so if Q is equal to 2 modulo 3, then here we have something that's not divisible by 3. And in particular, I can let's see. Yes, and so like in this picture, okay, let's make this precise. Let's call this map, which is not unique really, right? There's this guy has a ton of automorphisms, but let's choose one such map F. Then we can ask. Then we get this picture, right? This equation here translates on the map F to 1, but this just means, and this map is an homomorphism. So we can just plug out this guy. And now, since we're working in the integers modulo n, right, in this picture here, or sorry, the cyclic group of order q minus 1, we can write it like this, where of course this multiplication is now understood to be in the cyclic group of order n. And this equals 0. Let me see, is this correct? This should be correct. But this must mean that yes, I think this does the trick, right? Because yeah, okay, yes, we can just write this as I see. Okay, this is a little bit weird. Let me double check this. Let's see. Does the argument work? Yes, in the cyclic group, right on the right, sort of on the right-hand side of this picture here, you can really pull out this guy. Yeah, okay. Yeah, so what's sort of interesting is that in this picture here, since we're keeping track, we're also looking at, in principle, when we write down expressions of this form, we also allow for 0 elements to appear, non-invertible elements to appear. But then we realize, hey, actually, we are guaranteed that we're sort of staying in this multiplicative structure, right? I have here some non-invertible element, I raise it to some power, which will remain multiplicative. Right-hand side is, of course, is 1, so that also sort of stays in this multiplicative picture. And so this problem initially seems hard to solve because I also allow for to have 0 in particular. But then I realized, okay, since I'm sticking within this multiplicative structure and everything's invertible and nice, I can reduce my calculation to take place only in the multiplicative group of ZQ, integers modulo Q, and that simplifies the calculation, and I really just get this expression here. Okay, good. And now the claim, of course, is that we have to be a bit careful, right? Because this Q minus 1 is not a prime anymore, so we can get 0 divisors. So this must mean that either 3 is a 0 divisor, is 0 divisor, or f of a is a 0 divisor. Okay, but f of a cannot be a 0 divisor. Why is that? Let's double check. So this cannot be a 0 divisor because that would mean that in this case we'd need that um, let's see, the GCD of this with Q minus 1 is greater than 1, but a GCD of 3 and Q minus 1, which we know is just 1 mod 3. Yeah, that works out, right? Yeah, since this is a prime, okay. So 3 is definitely not a 0 divisor. Now I just want to double check why f of a is not a 0 divisor. That is not clear to me. Wait, is the I don't like this. Wait, I believe if one of them is not a 0 divisor, then okay, I'm slightly concerned now with this other case. Let me quickly check how long already this has been going on for. I'm not sure if I can see. No, I can't see. For the sake of time, I won't continue too much longer. Okay. I'm noticing I'm getting tired, so I won't make this too much longer indeed. But I would need to double check this. But I do remember that this was sort of the spirit of the proof. Yes. Okay. And so one thing that we notice is that the fact that 3 is a prime here, right? That is sort of important here, because that allows us to make claims like this. And this sort of is one of the obstructions that prevents this proof that I have in mind that I'm now working on to really give you tighter lower bounds. Because one thing that you might try is that, okay, if we can do it for square free integers, then maybe we can start adding higher powers. Well, first of all, that doesn't work, or at least not on a, if you just add, all integers that have go up to exponent, let's say 2 or 3 or some finite number in the exponents of your prime factorization, that doesn't really add any density. So if at least I remember correctly. So we have this weird thing that, if you look at the primes, then, if we look at the square free integers, then they have natural density 6 over pi squared. And then if you look at all integers up to like power 2, they contribute nothing, I believe. And sort of, I guess the hand wave approach to see this is that if you have some set that has non-zero asymptotic density, sorry, I've been saying asymptotic density, and I might be meaning natural density. Let me double check if I'm mixing up terminology here. Oh, okay, those are the same thing. Okay, good. That's good to check. Right. If you have asymptotic density that is non-zero, then, and it's also not equal to 1, I guess. Yes, I see. Okay, let's take one set that has asymptotic density, finite non-zero asymptotic density, and let's say I now look at its. I now apply some function to all the elements, such that, well, let's say I square them. Yes, let's say, that also doesn't work. Okay, maybe that's not true what I said. I should double check that. Okay. What I had in mind is that if you look at the finite, you choose some k and you look at all the prime factorizations that go up to that exponent, all integers that have a prime factorization so the exponents are below that number k, then that still has asymptotic density 6 over pi squared. But now, as I'm saying that, it does sound a little bit suspect, so maybe that's not true. I had in mind this would be one obstruction. Let me quickly sketch the argument. So let's say we can prove this, which I haven't really fully done, but I'm quite close, and I hope to finish that maybe next time. If we know the statement, or I guess this statement, and we know that S of n is multiplicative, which I haven't proved, of course, then what I can do is I can look at every square free integer. Now, a subset of the square free integer, of square free integers, will have at least one. Will have at least one prime in its factorization, such that p is not. Wait. Let's see. Yes, such that p is 2 modulo 3. And then when we calculate S of n, we get it factors because of the multiplicative structure, but none of these terms is divisible by any prime that it's 2 modulo 3. So as long as we have square free integers, such that there's at least one factor that doesn't have a prime that is 2 modulo 3, then we know that that integer does not divide S of n. And my claim, I haven't fully rigorously proved this, but I'm happy enough as this with the statement, is that the asymptotic density of the square free integers is the same thing as the asymptotic density of the square-free integers with at least one q is 2 mod 3. Yes. Then what I also want to do is show that, okay, the asymptotic density of, well, actually, let me use this here. This asymptotic density here, well, sorry, let me motivate this statement. Here, what we're saying is, okay, we have all possible prime factorizations, and in general, there will be the number of such factors appearing will be relatively large. And the idea is that it will be harder and harder to not have a prime in there that is 2 modulo 3. So of course, as I'm saying this, I'm realizing this is not very rigorous, but this is at least the level of rigor that I'm sort of happy to work with, or at least lack of rigor, I should say. So one would have to formally prove this. I'm not sure how to prove this. This might be actually quite messy, although there might be relatively general statements known on asymptotic density. So who knows? I'm wondering if one can use somehow the fact that there's a statement. Oh, I forgot the name of the theorem, but if you choose some integer a, then if you look at the residue clauses modulo a, then the primes are equidistributed, except sort of in the obvious cases. And so we know that there's the asymptotic limit. There's just as many primes that are 1 or 2 modulo 3. And I'm wondering if you could lift this to a statement like this. Okay, if I give you, if I sort of keep track of, if I look at n and I look at its prime factorization and I keep track of the number of times that I have primes appearing that are, oh, this is annoying. Okay, what I was saying was the following. I look at all the primes that appear, maybe including or excluding the multiplicity, and I keep count of how many times they appear, again, with or without multiplicity, that are of primes that are either 1 or 2 modulo 3, or whatever residue class, right? And I'm wondering if you still then get some equidistribution. That would make sense, and I would be surprised if this hasn't been proved. But maybe one can then use something like this. But as I was saying this, I realized, of course, we only are summing over or interested in square-free integers. So then one would also need to show that the statement holds in that case, and that's less obvious. Or I'm not sure if people would have looked at something like that. That's a lot more specific, it seems. Okay, that aside, let's now look at the following. So let's assume that this holds, right? Now, what I claim is that this is 2 times the ID of, well, exactly the same thing that are odd. And this is not too hard to show. I won't write down the proof, but the sketch of the proof is that we just exclude having. If we look at all square-free integers, then they sort of naturally fall into 2 classes, the odd and the evens, and we just only want to look at the odd ones. The reason why we want to look at the odd ones is because we actually already have a proof that even numbers satisfy the condition. So we don't have to use this method, this proof here, to cover those cases, because they would only cover a small number of cases, and that helps simplify the argument, right? And so we sort of use the part of the proof for half the numbers, roughly speaking, and then we have the proof that works for square-free integers with at least 1 q modulo, that is 2 modulo 3, and we could use them sort of separately. But no, I want to say no. I know that it works for all the even numbers, and separately, I'm going to apply this proof for all odd square-free integers that have a prime factor that's q is 2 modulo 3. Okay. So again, I won't prove this rigorously. So what does this lead us to? Well, we know that this quantity here is 6 over pi squared. That's of course a classical statement. So what we then get using this argument is that, okay, first of all, we have all even numbers. We know that the statement holds for those numbers. We had proved that in the previous video. And then we have the statement holds for all square-free integers. With the q is 2 modulo 3 factor in it, at least one, which we assume is equal to this, right? We haven't fully proven that. But then we need to just restrict to those that are odd. So then we actually get here just 3. And let me quickly check what this evaluates to. This is a half plus 3 over pi squared over 2, which is a little bit above 0.804. And this is sort of the best that I have gotten to so far. And I would still like to improve it, but there's quite some barriers. Like the approach that I used here, or at least the sketch here, I of course didn't prove anything, only goes up to it has sort of natural barriers. You cannot really extend this at least in a clean way, I found. And of course we know that there's counterexamples, and it's not really clear yet, where these counterexamples come from. We know that, of course, they cannot be square-free integers, at least one factor, that's the 2 modulo 3. I think the first counterexample is a long string of numbers that is only with primes that are q is 1 modulo 3. But it's it's not like that any sort of if we take any subcollection of those prime factors that we get a counterexample. So there's some, it's not clear where the structure comes from, or really what to exploit. All right, I think this is a good moment to stop.